And yeah, so the point was that if we go back again to the 2 dimensions and we write down the determinant of grad y as the dx1 dy2 dx2 minus dy1 dx2 dy2 dx1. So there was this trick that if y is smooth enough, and then we approximate Sobolev functions by this smooth function. So just we take the first derivative with respect to x1 in front of it, and we write down y1 dy2 dx2. So again, I mean, the first term is fine. The second derivative here is redundant, so we kill it by the second term, which will be y1 and dy2 dx1. So again, I can put this minus here and put plus here, and then I can write it as a divergence of some field V, where V1 equals, this will be my V1 and this will be my V2. So in particular, what you see that if you have if you have a 2-dimensional domain omega, and you calculate the determinant of grad y for y is 0 on the boundary of d omega, then this is 0. Because here you see you have the component, so even y1 would be enough to have 0. So whatever the function does inside the domain, it doesn't matter, but the determinant is always 0. And this weak continuity of the determinant, so let me recall again what we said. So we said if yk converges weakly to y in w1p omega Rn, p is bigger than the dimension, and omega is bounded and Lipschitz. Then determinant of grad yk converges weakly to that grad y in Lp divided by n omega. So we need Lipschitz domain simply because we use the embedding. So, you know, you can also generalize it a bit. So, but you need the embedding theorem works and so on. So now you say this is very surprising, but I mean, in fact, it's not such a big surprise because you can develop the determinant along the rows and use the cofactor. So I think you can, if you have a determinant of grad y, then you can write it as in n dimension. I think it's 1 over n gradient of y dot cofactor of grad y. And so these are two matrices. This is a dot product, 1 over n, because now I do the dot product, so I develop along all the lines, but the determinant is only 1, so I divide by 1 over n. This guy here is a gradient, so it's curl free. So this is curl free. Curl of gradient of y equals 0. And this guy, cofactor of grad y, is divergence free. And here the divergence is calculated, the divergence of a matrix is calculated row-wise. So you take the first row, you calculate the divergence. And this thing here is called Piola's identity. You can calculate it by brute force. If you take a smooth y, you calculate the cofactor and you calculate the divergence. But it's identically zero. And this helps a lot. So, and there is a result. Like normally when you have two weakly converging sequences, you take a product, and there is no hope in general that the weak limit of the product will be product of the weak limits. Because weakly converging sequences are oscillating a lot, and these oscillations can interact and spoil the result. But if one is curl-free and the other one is divergence-free, then it's different. Then the oscillations are sort of perpendicular to each other, and you can pass to the limit. And this is a general result which is due to Mira and Tartar, and it's called Differential lemma. So here I would just make a remark that it kind of comes from the Differential lemma. And it's Francois Mira and Lick Tartar. And it's used a lot in say, PDEs, homogenization, and various nonlinear analytical problems. So somehow, if you know the Differential lemma, then this result is not so surprising for you, in particular if you know the Piola's identity. So everything is connected in this way. But yeah, so we will now use this result. To discuss a bit a case P equal n. You know, P equal n means that the determinant is living in L1. And this already may indicate that there might be some problems because, you know, L1 is a special space where having a bounded sequence in L1, it still doesn't mean that I can pick up a subsequence which converges weakly in L1 because there is this issue with uniform integrability and so on. So let's make an example. What happens if we take P equal n? So the history is like that. So as far as I know, the first example that the result doesn't hold for P equal n is due to Ball and Mira in their paper in 1984. So this is the same ball what has this polyconvexity, and Mira is the guy here. I think 80s. They have an example for n equal 2, and they say this is due to Tartar. So it's in the paper and say that Tartar, you know, and then they publish it. So, and then I asked Tartar, and he told me no. So I don't know who is the. But this is a very complicated example on a square with sine and cosine. But I show you a new one which we developed with my colleagues in Prague, and it works in any dimension, and it's much simpler. So assume, so let's make an example. That, let me call it star here, doesn't hold. If P equal n, and I just do it in 2 dimensions, but you can also do it in any, because in fact the calculation is easy. So yeah, so take U in W12 of a unit ball with values in R2 and 0 boundary conditions on this unit ball. So this is a unit ball centered at 0. Now we extend U to the whole space by 0. So the picture is like that. There is this unit disk, 0 boundary conditions. We do something like that. And then we extend by 0 to the whole space. I still call it U without changing the notation. Now we construct a sequence. And the sequence is simply UKX. Like this. So what does the sequence do? So you see there's a k in the argument, so k will go to infinity. So this construction will get smaller and smaller, closer to the origin. And if you look at the gradient, this is k times gradient of u ukx. Huh? So this is the gradient is going to have a smaller and smaller support, and it will be bigger and bigger because there's a factor. So what you can show, first we show that if you do the integral over omega, you calculate UK x or 0, maybe the ball here. Then just plug in the what we have here. So this is the k times the gradient. So it's k squared gradient u kx to the power 2. The x, yeah, we do the change of variables. Very easy, just k times x. So you say y is kx. This kills this k squared here because we are in 2 dimensions. And you get, and then you inflate the ball, the domain. But because the function is extended by 0, it doesn't matter. So I get just this thing here. And this is supposed to be bounded because my function is in W120. And this is smaller than infinity. So the sequence is, the gradients are bounded in L2. And I have 0 boundary conditions. So I can use Poincaré to bound the whole sequence. So finally we, oh. Inequality and u equals 0 on the ball implies that uk in W12 is more or equal some constant, which is just this number for every k. So I have a uniform bound. So I can test now because I have for my u or y being u now for this example, I can proceed. So because everything is bounded on a ball, it's also bounded on a half ball. And we know that my determinant integrates over the ball to 0. So we know that the integral over the ball, 0, 1, determinant of graph u x dx equals 0. Because I have 0 boundary conditions. Now, we take D. I could write subindex nu, for example, but I will not do that. But I take it like that. I take x in the ball. Or let me put nu here. And I take a half ball. So I take a subset of the ball such that x dot nu is smaller than 0. And we pick up nu such that, so this is a unit vector, so this is a unit vector, so in S1, say, in 2 dimensions, such that if you integrate only over this d nu, the determinant, you get something negative. So the other half ball has to be positive, because the sum has to be 0. You construct a sum. I mean, nu doesn't matter. It only has to satisfy this. You can picture it. So why? But I show you. Yeah. So this is a ball. That is 0. This is the center. You take nu. This is a vector in this direction. And this is one half ball and the other one is here. So you take just a half ball, which is created by a plane with the normal nu. No, the center is 0. There is 0. No, this was just a cross showing that this is 0. So maybe I forgot it. So there is the origin. So this big. So this is a unit ball. So radius is 1, and this is a half ball. Half ball, like a. You take a plane, and this plane cuts the ball. This is the normal to the plane. Like if you take a melon and cut it by knife, you get a half melon. So. I mean, you construct. I mean, you can construct it. Yeah. You don't have. I mean, if ball is difficult, you can also take a square, because ball, in a way, it's just defined around it because we consider, say, Frobenius norm. But you can also take a square. No, because the integral over the whole ball will be 0. So if you are not extremely, if you don't have a bad luck day, you find a half ball where the integral is positive or negative. If you find it positive here, then you reflect your function. And then it's enough if you find, for example, a positive determinant on the integral is positive of one half ball. No, but then you take a different one. That doesn't matter. There exists, yeah. I don't care about a particular function. I just want one. I mean, in fact, You know, you can also do it for maybe a small piece than just a half ball, you know, it doesn't matter. So, I mean, this is, and then you inflate a bit or so, but, I mean, but it's just, I would say randomly, if you take some u, you randomly, and a plane, then you randomly get some non-zero integral. So this is, I would say it's almost surely, like people in stochastics would say. So now you do have, so assume you have this. And of course, on the other half ball, which I will denote d minus nu, and this is this one, so this was, so this is my d nu, this is my d minus nu. Then on the other half ball, I get that this is positive, because the sum has to be 0. So now what we do, we check this convergence on this half ball. So we take the limit for k going to infinity on this half ball, determinant of grad uk x dx. And I pass to the limit, but it's not so complicated because you can just write down what is it. So it's d nu. Now you look at the formula again here. So determinant is a two positively homogeneous function. So if I have a determinant of k times a matrix, I can take k squared in front of the determinant. And again, change of the variables formula kills this k squared. And because again, I'm inflating a half ball, nothing happens. So I just get d nu determinant of grad u x dx. And this is supposed to be smaller than 0. So now, what's the limit here? So we have to calculate the limit. So the weak limit, so the uk goes weakly to 0 in W12 of the ball. So we would expect, if we rely on this result, that here the limit will be 0. But this is not the case, this is something negative. Yeah. Is 0, and this is smaller than, oh, this is bigger than determinant of so that's the problem. I'm sorry, this should be 0. I made a mistake here. This is now smaller than 0 by our construction. and this is smaller than 0, but this is determinant of the limit. This is smaller than 0, but we expect to have 0. So the limit, the new determinant of 0 equals 0. So the limit should be 0, but in fact, it's smaller than 0. I got confused now with this. So it's a contradiction to weak-level semicontinuity. Because the guys go to 0, but the limit here, which you can also say it's lim-inf if you want, is smaller than 0, and it should be 0. Now this is a convergence in L1. So if you take the other half ball, then you get something positive. So then you show that in this, if you work on the other half ball, and if you take the limit for k going to infinity of d minus nu, so the other half ball of the determinant then this goes to determinant of grad u of x dx on d minus nu, and this is positive. And this is, so this is bigger than d minus nu determinant of 0, which is 0. So on the other half ball, you get sort of strict weak-level semicontinuity. And if you take the whole ball, then this sums up, and you get the result you expect. Because if you do this construction on the whole ball, so omega is a ball, then these two sum up, and then you get the right result by chance. So somehow you cannot really say what happens in case p equal n. You may have all results. You may have a counterexample to weak sequential Lowell semicontinuity. You may have not weak continuity, but really strict weak Lowell semicontinuity, or you may have what you want. So everything is possible. Everything is possible. Oh. Uh-huh. Good question. So we published this example in this survey paper in Science Review, and then I got an email from Sim Maor from Technion, and he told me that he read the paper and he came up with the example, which has also the positive sign of the determinant. So it's possible, but now I want to discuss a case when this is not possible, because this is good for elasticity. So just to tell you why, why this happens. This happens because the sequence, where do we have it? Here, is such that it concentrates on the boundary of the domain. So the sequence of the gradients is not equi-integrable in L1 if you take the second power here. So it's not too equi-integrable if you want. And the concentration happens at the boundary of my domain. And this makes it a problem. If this happens inside my domain, then nothing happens and I'm fine. But at the boundary, this is always a trouble. And from the boundary, from one side you get something nice, and you get something bad from the other side. And it's very hidden in the example by Ball and Mira, or Tartar. The boundary of d nu, and also d minus nu. So this gives you some sort of implicit results. For example, that if you have a sequence like this, on this half ball where you have this concentration, so the case 1 happens, then you cannot extend your sequence to the other side of the ball in such a way that the second power of the modulus is equiintegrable. Because if this would be a case, then I have a problem here, because I would get 0. And then on the whole ball, I wouldn't get 0 for the integral. So this is like 84, this ball mirror, and then we have this 2017, and then there was like 2018 Mauer, I think from Technion, positive determinant. In between, in 90s, Stefan Müller, I think it's 90s, showed the following. Assume that UK goes weakly to U in W1N. So you take W1N, the critical case, and that determinant of grad UK is bigger or equal than 0 almost everywhere in omega for every k. Then determinant of grad UK converges weakly to the determinant of grad U in L1 K Rn, where K is compact and K is a subset of omega. So if you control the sign of your determinant for every element of the sequence, and you don't go up to the boundary of your domain, then you have the result. And he even showed that, so this means, because you have weak convergence in L1, there is this Delavallee-Poussin criterion, which tells you that there is a higher integrability of determinant. So, in particular, it means that the determinant is not only bounded in L1, the sequence, but in something a little bit better. So, So this also implies that if you take psi of determinant of grad UK over over K, then this is smaller than plus infinity or smaller than constant for every little k, and this psi is superlinear at infinity. This is de Laval-Poussin, but he identified psi to be psi of x or so psi over x is x times logarithm of x. So it's a superlinear function. So, you know, from L1 V convergence, you get that there is a function which may depend on the sequence and so on, but he found the one function which holds for every sequence. And it's a famous result because he got a prize for this result in the first Congress of European Mathematical Society in the 90s in Budapest. And this is also important that you don't really integrate over the whole domain because you have to avoid concentrations in the boundary. Again. You can also do this, prove this result if you have an opposite sign here, so negative. But because the inspiration came from elasticity, then here the so this is a result which is called higher integrability of determinant, and to get this function is difficult. To get just this result, that there is L1 V convergence, is not so difficult, but still quite involved. So now I maybe erase the blackboard. And so you see Ulysses. Ah, there is nothing. That's good. So now I want to give you a result which will be then used for this polyconvexity, and it's quite general, and also the proof is a bit maybe involved, but maybe not so much. I hope we will be able to somehow go through the proof a bit. So this was the determinant. Yeah. So again, just want to list all the assumptions. So assume, so this is like a proposition. Let H, which goes from omega times Rd, or Rd times Rm to R maybe plus infinity, satisfies the following. Satisfy the following. So one is that H, if you look at it as the function of one variable, so you put he, z, and v, then this is a function from omega to R, and this is supposed to be measurable. For all z and v. Now we have 2, and then we move the dot further, so we take x dot and v. Now we put only 2 dots here, and so this goes from Rd times Rm and I say it's continuous. It means, because it can take the value plus infinity, that if your arguments are going somewhere, then the function along these arguments also goes somewhere. So also maybe to plus infinity. And or I could also replace it by this lower semi-continuity, but maybe this is easier. And now if you take x and v, and you just look at it as a function of the last variable, so this goes from Rm to and I assume that this is convex in the last variable. And the continuity holds for almost every x. And this is for almost every x and all v. So we have these main assumptions. So convexity in the last variable, continuity in last 2, and measurability in x. So it's like a Carré-Theodori integrand if you want. So now assume that you have zk is a sequence of measurable functions such that zk goes to z. Almost everywhere. So there is some pointwise limit of those in omega. And let Vk goes weakly to V in L1 of omega with the values in Rm. So it's a V convergence in L1. Finally, let H X Vx and Vx, or maybe I just do it this way, so I say assume let H be non-negative, so this maybe it's easier. Then lim inf for k going to infinity of H, X, Zk, Vkx, Vx is bigger or equal than H, X, X, Vx, Vx. So this, if you call this a functional, then this is a, again, sequential weak-level semi-continuity result for the functional. So some people call this Eisen lemma, and some people call Eisen lemma only a part of the proof. So the result was, there are various versions. I think one is from, due to Berkowitz from early 70s. Just to give you some time frame. So this is the result. So what you see here that if we have pointwise convergence, then we don't care about convexity properties. We just need continuity here. And when we have only weak convergence, then we need convexity. Similarly, like in this result last like on Monday. So this is so the proof goes like this. So the proof goes like this. So first of all, we again assume that we take a subsequence such that the lim inf is already lim here. We consider, without loss of generality, that lim inf is just lim. You are already experienced, so you know. So now minus infinity is out of question for L, and then we call this lim, and this is L. So we call the left-hand side L for sequence. So you know that minus infinity is out of question because we have non-negative integrands. Plus infinity would be only helpful. So we have to consider the case that L is real. Or so it's positive. Or 0. So this is a bit easier than last time, but just a little bit. And so we assume that L is smaller than infinity. And now so we have this, and now this is what so now the proof will be like that we assume something more and then we remove it, this assumption. So in the first case, which I maybe call A, assume that gk goes to 0 in a measure. We can assume it because I didn't tell you yet what's gk, so why not? But gk will be the following. Gk of x is h at x, gk vk of x minus h of x z of x and vk of x. So, and x is in omega. So the difference is, in the difference here you have the z, this is the limiting value, and k in v is still there. So you just do the difference of those two. And if we assume now for a moment that it goes weakly, that it goes in measure to 0. So again, we can take on Monday, we can take some epsilon positive and assume that you take epsilon positive and this there is k0, which is a natural number such that for every k bigger than k0, hx, zkx, vkx is smaller than L plus epsilon. This is the property of the limit. And because we have convexity and we have weak convergence, so the first thing which comes to our mind is to use the Bazoo Lemma again, like on Monday. So we define here Wj, and this will be a sequence defined by the following. So you take k is between j and infinity, lambda j k vk. And I recall that only finitely, for given j, only finitely many lambda jk are non-zero. They sum up to 1 for given j, and they are non-negative. So it's a convex coefficients, coefficients of the convex combination. And so we apply the Bazoo Lemma to this sequence, and we know that Vj goes to V strongly in L1 of omega Rm, and it means for a subsequence also pointwise. So I do not label, but say also pointwise. No. So now we denote something by, so now what we do, we say alpha j of x. This is my sum of lambda jk for, you take this from j to infinity. So these are the convex coefficients. So we have there, and this is x dk x and vkx. So you take, you denote this by alpha j for, and we know that this is bigger or equal than 0 because these integrands are non-negative. Now alpha is the lim inf of alpha of x will be the lim inf of alpha jx for j going to infinity. And again, this is non-negative. And so this non-negativity, lim inf, and pointwise convergence will be used to apply the Bazoo lemma. Which tells me that 0 is more or equal than alpha x dx over omega, and this is smaller or equal than lim inf integrals alpha j x dx, and we look at the definition, and we see that this is smaller or equal than L plus epsilon. Well, this was my limit, so the definition of alpha j is here. So again, we integrate over omega. So this was the Bazoo lemma. And now I take alpha j hat. This is almost the same like alpha. Only what I do, I fixed z. Instead of zk, I put there z. So this is my alpha j. Yeah, I think so. So now the difference, if you look at the difference of alpha j and alpha j hat, so the coefficients remain, but then you have a difference of this and this. So if you look at the definition of G, in fact you get this as a coefficient times GK. So by our assumption, A, we have that alpha j or alpha j minus alpha j hat goes to 0 in a measure, but I can take a subsequence which will be pointwise converging to 0. Almost everywhere in omega, again for a subsequence. So, but now if you look at what happens with alpha j, so alpha j had at x, this was already defined here. And now I have a convex function in this, so this is fixed now, this is x and z, so there is no k, this was important. So now I use convexity and I make it smaller if I put these guys here. So this will be, so I say that this is, this, you know, what is it? So this is bigger or equal than h at x, z of x, and wj of x. Huh? And this, here we used convexity. Of a, x, z, and dot. So this was used. So now we do the pointwise convergence. So this goes pointwise to alpha because we have this difference. So this goes to alpha, alpha x, because we know the pointwise limit is the same of both. This was, this comes from this G. The pointwise limit of both is the same, and so the alpha j goes to alpha, and this is, and this, the right-hand side goes to hx, zx, and v of x. Because this is now converging pointwise too. So I have also here bigger or equal. And now we go to this place where we apply the Bazoo Lemma, and we see that alpha is bigger or equal than this animal here. So we can put it here, and we get a result. So the result follows from this. So it was a little bit like on Monday, but now we had a special form of a functional, because if you want to get a kind of more detailed result, you cannot just work with I of u, but you need something more concrete. And yeah, and again, the Bazoo Lemma was a key issue here. So now we have to remove the assumption that the gk goes to 0 in a measure. And this is based on say 2 lemmas, or no, 1 lemma. And the lemma, again, some people call it Eisen lemma, but I found more references that they call it Arcela-Young lemma. Marcella Young. So Young, I don't know whether this is Young, like Elsie Young, or his mother. Probably his mother. No, this has to be his mother because I think Marcella, this is like beginning of the 20th century, and Young, Elsie Young was 30, so I think this was the lady who has the Young inequality also. So the lemma is the following. So let omega be in Rn. Be measurable and such that the measure, the d-dimension, the n-dimensional Lebesgue measure is more than plus infinity, which will be our case. So for us, always omega is bounded, say, Lipschitz domain. And let omega indexed by k be a sequence of subsets of omega such that the measure, the n-dimensional Lebesgue measure, is of all of those is bigger or equal than some epsilon, and this is positive for every k. Then there is a subsequence of omega k, which I will not relabel again for simplicity, such that the intersection of omega k is not empty, and the Lebesgue measure of points that belong, of points of omega that belong to infinitely many omega k's is at least epsilon. So that's the result, which also some people call Eisen lemma. Have you ever seen such a result? So this result was first, I mean, the first trace I could really find it was some Russian book by Krasnoselsky, or paper, Krasnoselsky and some Russians, in 1968. And so this is the first proof there. The book is in Cyrillics, in Russian. But there is a later proof by Lughaus of this. And maybe I give you the proof by Lughaus. And so Stefan Lughaus. So what you define, you take the characteristic function you take chi of x, and this is the limit for maybe L going to infinity of the sum k equal 1 to m, no, to L, the characteristic functions of omega k x. So you take the limit, and then you take a sum up to L, and then you take a limit for L going to infinity. And now you take something which I call dk, and this is defined like that. So you take omega k unified omega k plus 1, and so on. So this index here is always the one you start with. So you see that dk plus 1 is a subset of dk. So they are nested. And now we know that the measure of dk is at least epsilon. The dimensional Lebesgue measure of dk is bigger or equal than epsilon by the assumption. And so the measure of the intersection of dk is in this case the limit for k going to infinity of the measure and this is also bigger or equal than epsilon. And if you are there, then the characteristic function, so in particular is plus infinity on this intersection. So the proof in other sources not look so in fact there is a paper by Eisen from 78, I guess, when he just mentioned this other proof by Lughaus. So I think it was not published by Lughaus anywhere. It's just mentioned in the other paper. And then the other proofs are also not so complicated, but this one is so there is a proof where you do it in 2 steps. First you show that there is non-empty intersection, and then you have to estimate a measure. This is done in the same line. So yeah. And now maybe we will not need this, so erase it. Maybe we keep the statement still and So now the last piece will be this application of this lemma to prove that gk goes to 0 in measure. And again, so the argument is so we show that the assumption A holds. So you do it by contradiction. So assume that gk doesn't go to 0 in measure. So this means that there exists epsilon positive and delta positive such that the set mk, which is defined like this, it's x in omega and hx zk x vk x minus, there's no, kx minus h x dx dx is bigger or equal than epsilon, and zk, we know zkx goes in this point to z, so it's convergence almost everywhere, so I pick up a point when this happens. And we know that h is continuous, so we assume that this is a point because this is for almost every x that h x dot dot is continuous. So this is the end of the definition of the set. So this set it holds that the measure that the d-dimensional Lebesgue measure of mk is bigger than delta, bigger or than delta. So this is the contradiction, the beginning of the contradiction argument. So assume that this is not true. So we have this kind of condition. Oh, yeah, you are right. There is Vk. I'm sorry. And now what you do, you say, okay, so we know that Vk goes weakly to V in L1. So in particular, so this implies that if you take integrals of Vk, then these are bounded. These are bounded by some constant which I call C. Or say every k, we can assume that this is for every k. And also because this right-hand side L is supposed to be in like a number, so we also assume that H dk x and vkx dx. This is supposed to be non-negative, so this is also bounded by this constant. So now we can define another set, which I call nk, and this is x in omega. And now you say, okay, I want points where vk of x, so the set is indexed by k, in the modulus is bigger than 4k, for c divided by delta. So c is this constant, or this guy here. The k of x, vk of x is bigger than 4c divided by delta. Or so now the measure d-dimensional measure of nk must be smaller than delta half, because otherwise we would break these bounds. So now we take points that are here in MK, so the contradiction is here, and they are not here. So these are those that this is smaller than 4c divided by delta, and this is smaller than 4c divided by delta. So, and I denote by mk, tilde the set mk minus mk. So the set k, the Lebesgue measure is at least delta. This is smaller than delta half. So this one has to have a measure at least delta half. So yeah, it's at least delta half. And now we use the lemma we proved for these sets. And we say finally M is the intersection of MK tilde, and we know that this is not empty. And the measure, the dimensional Lebesgue measure of M is at least delta half. And this is due to Arcela Young. But if X is in M, then we have that Vk of X for every K is smaller than 4K divided by delta. We know that this is non-negative, so X and Z, Kx, Vkx is smaller than 4K divided by delta. Here is K. Oh, so sorry, I have to say C. This is the constant. This is the constant we had there. So now we have this. So we pick up a sequence, a subsequence that goes for this given X to B, to some limit, and also here. And we know at the same time that this is true. But it's the and this is and so we have moreover we have and and this is a contradiction with the continuity. So this inequality here which I denote star 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 is in contradiction with continuity of h x dot dot. So it was a bit technically involved, I would say, but so this is the general result, quite general result, which is used in many applications. And maybe I will do one application just to mention it using this polyconvexity, because in particular the functional which we have here, I mean, if you call this functional, which is a functional in Z and V, it's non-convex, because we don't assume any convexity in this variable. So we moved from convex functionals on Monday to non-convex functionals. So that's the achievement. And then if you want, we can make a bit break for, but I don't know if we leave the building, Ulisse, what do you think? Can we get back again, or do we need to be checked? We would need some stickers, like a sticker for the day. So I don't know, I mean, if you don't want to leave, then maybe we can go on as you want. So, because to stay inside maybe doesn't, because we have to have masks anyway, so. Oh yeah, okay, so if you want, if there is a general agreement on that, I'm happy to do that. Maybe I do the application and then, because then we change the topic a bit. So a typical application you can have in mind, and you can use this kind of proposition is the following. So you have j of y, and this will be the integral over omega wx, y of x, gradient y of x, dx. And this is a function which will be measurable here and continuous in those two. And we assume x, y, and dot is polyconvex. So it means again that this can be written, and this means that and the determinant of f in 3 dimensions, if we are in 3 times 3, if you are in 2 times 2 case, you can forget the cofactor, because in 2 dimensions, cofactor matrix and the original matrix are the same. They are only rearrange the entries. So if you know something about f, you already know something about the cofactor. And so here you need convexity. So now we would apply our proposition. So this will be, this is my x, this is going to be my z, and all this is supposed to be my v, because I have convexity here. I assume measurability here, continuity here, but no convexity. And then what you want to prove is that you take y in some Sobolev space, and you take y, k converges to y in W1P omega R3. And you take, let's take P bigger than n again, so because we did it before. You can also generalize it a bit. So if you have this, then what we know that yk goes to y in C omega closure uniformly. So in particular, have a pointwise convergence. So somehow we don't have to assume the pointwise convergence here, because we get it from this setting of the problem. And so this is the lim inf of j of yk for k going to infinity is bigger or equal than the j of y. And here we have to also assume that this is w is not, if w is non-negative. So that's the result you can apply it to. So in mechanics, typically you don't have this dependence of y on y, but you can get some information about y from the boundary conditions, which are usually there, because if you do some experiment on your body, like the sponge here, for example, you pull it or you deform by boundary conditions, so you fix it somewhere. So you have a gradient information from the energy density, W, and then you have the boundary conditions, and it means you can also get a bound on y in some LP space, again through Friedrich's inequality or generalized Poincare inequality, and then you get a bound on your minimizing sequence in the Sobolev space. What is more involved is to deal with the determinant, because sometimes you prescribe the boundary condition on a part of your domain, but we have to work only with energies that have positive determinant. And it's not always clear whether you can extend your boundary condition inside your domain in such a way that the determinant of the gradient stays positive. So we know it from this Marshall's paper, what are the trace spaces for the Sobolev spaces. So if you know that on the part of your boundary you have a function which has some quality, you can extend it inside as a Sobolev function. But if you have this extra assumption on a positive determinant of the gradient, it's not clear anymore. This is the issue. So in many cases, you have to assume that your set of admissible deformations, which prescribes boundary conditions and also the sign of the determinant, is non-empty. And so this is how you do that. And then you prove the existence of minimizers simply by coercivity, and this is the main key issue here. And if you want, we can just open the window now for 10 minutes, and then we will go on. Up to now, we've talked about sufficient conditions for Lauer semicontinuity. So maybe it's time to say something about the necessary condition, at least in some case. So let's take our functional J of y. And I here take W of grad y. And omega is it's a bounded domain in, say, NR D, and my y now can be from my y will go from omega to Rn, and so it doesn't have to be a square matrix, the gradient, but it can be just arbitrary dimensions. And the question, W will be a function, so suppose W, which is defined on matrix, is n times D to R is continuous. And the question is, what should I assume about W if I want that this function is weakly sequential Lauer semi-continuous in some Sobolev space? So I take a special situation, and I will look at Lipschitz functions only, because they are very special. So I just want that my functional is weakly Lauer semi-continuous along Lipschitz functions for the best possible sake. And to isolate a necessary condition, which means I take a sequence and I assume that there is this property of Lauer semi-continuity, and then hopefully I get something from I. So the question is the following. So we have this omega, so this will be my omega, and I assume I can put there a unit box, or Q, maybe not unit, but this is a Q, a little box, which with faces which are aligned with the coordinate axis. So this is omega, this is Q, and then the axes are here. And I take and I take y, is it y tilde? Then just to get, yeah, I take y tilde, which will be in W1 infinity, 0 boundary conditions on the cube, and the values are in Rn. Function like that. So it's a Lipschitz function which has 0 boundary conditions here, and is defined like that. And because it's defined only in the cube and it's a 0 boundary conditions, I can extend it periodically to the whole space. And again, I will keep the notation. So my y tilde is everywhere because I cover the space by q's. Everywhere. And extend periodically. So we have y tilde, so now we need to get a sequence to test something. So the sequence will be yk tilde of x, and this will be now a bit different than before with u, but this will be k to the 1 over k times 1 over k times kx. So kx is here, but it's a 1 over k. So in particular, as k goes to infinity, this is a Lipschitz function bounded. So this means that this goes to 0. Goes to 0. And I know the uniformly. And I know, because this is a Sobolev function, then I know that yk tilde goes weak star, if you want, weak star in W1 infinity to 0. So now we take a matrix A in R n times D, arbitrary, fixed, arbitrary matrix, and we define a sequence yk is defined the following way. So it will be Ax, affine function, if we are outside the cube, so in omega minus q, and it will be Ax plus yk tilde x if you are in the cube. So you see that at the boundary of the cube, you are fine because this is 0 there, this is Ax, and this is Ax. So in particular, just if you want to do the Sherlock Holmes quick test, whether this is a Sobolev function, then you see that there is a continuity. And so because this guy went to 0, this guy goes to Ax. So we know that yk goes weak star in W1 infinity to A, and I put here dot, because I shouldn't put there x, otherwise it will be a value of a function at x. So this means that this is an affine function. So in other words, so yk goes weakly star to a function which assigns to x Ax. And affine functions are good because to evaluate the integral on the affine function is easy. So now we assume that the lim inf of j of yk is bigger or equal than j of let me call this y of x, j of y, for k going to infinity. So we assume, and now we will write this down. So this means lim inf for k going to infinity. And now what's j? So if you are outside Q, then it's easy because this is just AX. So this will be the measure of the d-dimensional Lebesgue measure of omega minus Q times W of A plus the integral over the cube and this will be W of gradient of yk x, but here you look at it, so it's A plus this one here. I can already put it there, so it's A plus yk tilde x dx. Now we say what's yk tilde. This was defined here. And we know that the gradient is so we plug it here. So again, we have the same term, but there is no limit even, so it's omega minus Q W of A plus now we do the change of variables. So we say this will be my other variable z, if you want. And this integral will be the same like you take k times the q, then you get 1 over k to the power d. And here you take, there's a gradient missing. So this is the same because of periodic extension. But you divide by k, and this is symmetric, so this is just like if you integrate only. This is like if you integrate only over q, and then you take a easy. Yeah? So, and this term, this is here, and so if you want, we can also, so we have this term plus this term. And this is supposed to be bigger or equal than the limit, but the limit is j at y, and y is just a times x, so this will be just the measure times w of a. So now you see that you have a piece here. It's a omega minus q, and there is omega. So what remains, if you subtract this, you get just integral over q. So finally, we have that Lebesgue measure of Q times W of A should be smaller or equal than the integral over Q WA plus gradient Y tilde of, and let me go back to X dx. And this should be true for every Y tilde, which was a Sobolev function with the zero boundary condition on Q with the values in Rn. And also the matrix was arbitrary, so for every A in R n times D. So this is the condition, which is a famous condition. It's called Meyers quasi-convexity. And it comes from 1952. And I say Meyers because there is other notion of quasi-convexity in optimization theory, namely the convexity of the sublevel sets. So sometimes when you Google quasi-convexity, you get this other notion, and then you can. So this is so this was isolated by Meyers in 1952. And so we see that in this case, it's a necessary condition for V-Clover semi-continuity of the integrand functional. And because I had a very special function, so even if I'm working in W1P, I can also take W1 infinity as a test function. So this is a necessary condition also for problems when I have a P different from infinity. I think he called it quasi-convexity. Yeah, and no, maybe this somehow he might anticipate that because there is already a notion, then the new one will be called after him. I don't know. you know, so this is a notion of quasi-convexity, which is difficult to verify, because think about it, I give you a function and I say, tell me that this is quasi-convex. We have to verify this inequality for every test function and every point. Difficult. It's again a variational problem. You would have to minimize the right-hand side over every y if you fixed A and then go on and go on. So what you can do easily is, if you are not happy with the zero boundary condition, then you can say, I can also rewrite it as the left-hand side remains, and this is more or equal than the integral over q, w of grad p of x dx, where phi will be a w1 infinity function, q Rn, such that instead of 0, I say phi of x is Ax on the boundary. Because you say, I write this as a gradient of this phi. So I first put Ax and then this one, and then this will be my, so then it looks like that there is no A on the right-hand side, but the A is hidden here in the boundary condition. So that's, now the other question you may ask is, how about if I take a different q here? Would it make any difference, or are there some functions that are quasi-convex only with respect to this q, or is it a general condition? So this condition is independent of q. In fact, you can replace q by any Lipschitz domain, and it doesn't matter. So once you test it for one domain, then it holds for every domain. And the reason is that you can, if you have another domain, assume this is your q. Now we zoom into q, and then we take another domain, q tilde. No, maybe I put q tilde outside. Here I put q tilde. So what I can take a point. So I take a point A in RD and epsilon positive, small, such that A plus epsilon q tilde belongs to q. It's a subset of q. So q is open, so I can do that, and then I move it here. Now I do my calculations on the original q. So this means if you take y, which is here, so assume that this is 1 infinity, 0 boundary conditions on q tilde with the values to Rn, and you extend it by 0 to the whole space. So now you can calculate the integral. So you calculate the integral over A plus epsilon q tilde of W A plus gradient of y, and you take here x minus epsilon, no, x minus A divided by epsilon dx. This will be on this little domain, so this will be my copy, scaled copy of q tilde. So this is A plus epsilon Q tilde. Here you zoom in again. And on the rest, you say this will be just my W of A, because there is Y extended by 0 times the measure, d-dimensional measure of omega minus A plus epsilon Q tilde. And this has to be bigger or equal, because now I work on the original domain, then W of A times the measure of Q. And I think the omega should be replaced by Q. And again, you do the change of variables formula, and you get the same result for Q tilde. So this is independent of the domain, which is good. So look at this condition. So the right-hand side contains A plus the gradient. If you integrate the gradient over Q, then the integral of the gradient over Q is 0, because Q has 0 boundary conditions, or the Y has 0 boundary conditions. So you take a matrix A, and then you calculate the integral over various perturbations, but the perturbations are 0 in average. So the average of the right-hand side argument is again A, and the perturbations are only gradients. So this is, if you have a general matrix there instead of a gradient, then it would be convexity. But now we have a special fields, namely curve-free fields gradients. And this makes a difference to convexity. So what we know, it's a necessary condition for V-clever semicontinuity. So if I take a finite valued function continuous, which is polyconvex, then the polyconvex functions already have to be quasi-convex, because polyconvexity was a sufficient condition. So polyconvexity implies quasi-convexity. If you assume that you have a function, say V, which goes from R n times D to R, and V is convex. So in particular, it means if you take V at A plus gradient of Y of X for a given X and given Y, then this is bigger or equal than V of A plus some linear term, which will be just say, let me call it G times gradient of Y of X. So this is the property, and this is a dot product. So if you want in matrices, this is a dot product. So somehow this is a property of convexity. So there is an affine function below this. So now we integrate this over Q. And because this has zero boundary conditions, then this term disappears. And I get exactly the definition of quasi-convexity. So it means that convex functions can be easily shown to be quasi-convex by this argument. And of course, because we know that polyconvexity implies quasi-convexity, so and convexity implies polyconvexity. So we have a chain which says convexity implies polyconvexity. And this implies quasi-convexity. If you are in dimension such that you don't work on matrices but only on vectors, so it means that either n or d is 1, at least one of those, then you have matrices which are just row matrices or column matrices, and everything is the same. Because here you have a gradient of a scalar valued function. Polyconvexity on a row matrix, this is just elements there, what else you can have there, and so everything coincides. If the minimum of d and n equals 1, then the notions coincide. Another property of quasi-convex functions is that you sometimes it's better if you don't work with fixed boundary conditions like 0, but you have something else like periodic boundary conditions. So indeed, there is a result which says if W goes from n times d to R is quasi-convex, and continuous, then for every matrix and every test function phi, which will be W1 infinity 0, 1 to the power d periodic. In Rd, Rn, it holds that W of A is more equal than, here you integrate 0, 1 to the power d W A plus gradient phi x dx. So phi is 0, 1 d periodic. So you take this is the unit cell, and then you extend it periodically everywhere, so to the whole space. And again, because of periodicity, the gradient of phi, if you integrate it over 0, 1 d cube, disappears. So the proof is very, in fact, this is, and of course the opposite implication is also true, because if you have periodic test functions, you can always take zero boundary conditions. This is also periodic on this cube. So you get also that this is the same. So if you have this inequality satisfied, then it's also quasi-convex. The proof is as you would expect. I mean, you know it holds for zero boundary conditions. Now you have non-zero boundary conditions. So in this business with quasi-convexity, this is I would say, everyday bread to use some cutoff function. You cut down the function close to the boundary to zero. You show that it holds. And then you pass to the limit with the thickness of the rim around your boundary. So that's the idea. And this idea also is the only one we have usually, and it also brings many difficulties. So this is our Q. This is our Q. We take a function. We have our phi. So we take phi k of x. This is again 1 over k phi of kx. And then we take eta L of x. And the eta L, so I take a kind of a rim here. So the thickness of this, the thickness will be 1 over L. And L will go to infinity. So eta x will be 1 inside here. So let me call this maybe Q is the subindex L in a QL. And this will be 0 on the boundary of the big cube. So you go from 1 to 0 here. So the gradient of eta L is bounded by something, some constant times L. Because on a piece which is 1 over L, you have to go from 1 to 0. So the gradient grows with L. You take the function eta L phi, okay, and this function has zero boundary conditions. Has zero boundary conditions on Q, because it's cut. So quasi-convexity, by the definition which was there, holds for this particular multiplication. And now you calculate the gradient. And because we assume continuity, so the condition, contribution from this rim is negligible if L goes to infinity, because it's 1 over L. And because we have this sequence which goes to 0, so we use also that phi k goes to 0 strongly. And so it allows me to show that, in fact, what is important is only the integral on this domain. And then I pass to the limit and I have it. So that's the idea. how you proceed. But it's again a bit, you have to calculate the gradient of this, which is 2 terms, but it's not so difficult. So you can try it, maybe like a little homework assignment, if you can do that. But I already can tell you that if you think about how we proceed, that we do this cutoff function, that it's good for general function, but if you, for example, want to keep positive determinant, then it's already difficult, because once you do this cutoff function, then it can destroy the sign of the determinant. So it's not really useful for applications in elasticity, because you really cannot keep the determinant positive. But we can use this property for periodic functions to something quite interesting. So, because quasi-convexity is very difficult to verify, people were after some easier conditions, which would be like the necessary conditions for quasi-convexity. So I can maybe check something, and then if I don't succeed to check it, or if I show it's not true, then I can say that my function is not quasi-convex. And maybe I get something simpler. And the way how you can get some necessary conditions is simply to take some test function here and just say, I don't want to do it for every periodic, but I do it for some special. So we do some special now. And the special function will start like that. So I take the interval 0, 1, and I take some lambda in this interval. So this is my lambda. And I take a function which will be in this portion. This function will be, so I call it chi of s, and this will be, I think it will be 1 minus lambda on the, if s is between 0 and lambda, and so it will be lambda times 1 minus lambda. So this piece is 1 minus lambda, so here I put minus lambda. If lambda is more or equal than s, and this is more equal than 1. So here I have 1 minus lambda, so it's something positive because lambda is between 0 and 1, and here I have minus lambda. And the aim was to get something that the integral vanishes. So the area here is the same, like, so this was 1 minus lambda. So 1 minus lambda times lambda is the same like lambda, yeah. So this should be like this. So I take this function and I extend it periodically again to the whole real line. And so lambda is something between zero and 1. Extend is height periodically. R. And I take a special, now take A in, you take A in Rn and P in integers to the power D. So it's a vector which has integer coefficients, components, sorry. And I construct my phi of x to be A times the integral 0 times x dot b from this function I s yes. Oh, that's the function. So the gradient of this function is the function chi at x dot b times a o times b. You know this o times, so it's a matrix of rank 1. So a o times b is a matrix which is called, it has components ij, and this is a I and bj. I call it O times because this is a name in LaTeX. Students in Prague call it bulb, because in electric schemes, this is a sign of a bulb. So they say A bulb B. So to bring you some notation from the east or west. So this is like this. So what we see, it's a rank 1 matrix. So it's a matrix which has a rank 1 if A and B are non-zero. This function, because B was taken to be periodic, is to be integer, is periodic on the unit cell. So it's an admissible function to be put there. So let's plug it there. So what we also see here, that because it's a periodic function, the gradient, if you calculate it over 0, 1 to the power d, gradient of phi x dx has to be 0 because it's a periodic function. Now the gradient, if you look at this, it only, so this function takes either value 1 minus lambda or the value lambda. But the gradient is either lambda okay, so how should I do it? It's chi of s times of x dot b, a o times b, Bx. So this is 0. This is supposed to be 0. And so the portion of, so it's, so this has a unit measure. So now I take a subset which have a, so this is a subset. So let me call it Q tilde of lambda times AO times B plus the integral over Q minus Q tilde of the other value is lambda, and it was, no, this was minus lambda, I'm sorry, and it was 1 minus lambda of AO times B. And so this gives me the portion. So the measure of this guy is lambda, and the measure of this guy is 1 minus lambda. So the measure of Q tilde is 1 minus lambda, and the measure of Q minus Q tilde is lambda, because they have to sum up to 1. So now you plug it into this definition, and you say for a given function A, for a given point A, you have W of A is smaller or equal. Now you have this piecewise constant gradient. So it's a portion when the gradient is lambda times this. So this is lambda times W n A plus 1 minus lambda AO times B, and this one, yeah, plus 1 minus lambda W A minus lambda AO times B. Oh. So that's the right-hand side evaluated. This was for B integer, A arbitrary. Now we go for B rational. We write a B rational as a fraction of two natural numbers. So this was for every B natural or integer and A general. Now we go for B rational, simply that if my B is rational, I write it as B1, Bn with some common denominator. And I prove it for rational numbers. Then I pass to the limit using the density of rationals in reals to show it for every real. So finally we get that this holds for every A in Rn times D, for every A in Rn, and every B in Rd. And this condition including these conditions is called rank 1 convexity. And geometrically it means these two matrices which you plug in as arguments of your W, they differ by a rank 1 matrix AO times B. And otherwise it's a normal convexity, but only with the restriction that endpoints of your interval have to differ by a matrix of rank 1. So maybe I can, and every matrix of rank 1 can be written as AO times B. So somewhat this is equivalent, like if you say so you can say W, which goes from N times D to R, is rank 1 convex if for every lambda between 0 and 1, and for every A1, A2 in R n times D, rank A1 minus A2 is smaller or equal 1. So let's assume also that maybe they might be the same. It holds that W lambda A plus 1 minus lambda A1 A2 is smaller or equal than lambda W of A1 plus 1 minus lambda W of A2. So this is an important extra assumption. Otherwise, it would be just convexity. We are almost there. So you can check, for example, that this holds with if W is a determinant, that it holds with equality. You can just check it in 2 dimensions, say. This also means that if you take a function of one variable, T, W A plus T O times B, T A O times B. So you fix A, you fix little a and little b, and you look at it as a function of one variable, T. Then this function has to be convex. So rank 1 convex functions do not have to be convex, but if you are at a point and you take a line in some rank 1 direction, then you go, and you feel like on a convex function because you are following the convex piece. And I think it's 12, so let's meet again on Friday.